Good morning, Ma. So I think you are able to hear my voice and you are able to see the screen. Okay, screen కనిపిస్తుంది Ma.
Yes, sir.
Okay, Ma. So, next we are going to study the four. I mean, first chapter. I mean, first topic of fourth chapter, that is about DSC. So in this DSC, we are going to study the principle, thermal transition, advantages, disadvantages, instrumentations, applications. If possible, we'll see with some interpretation. Okay. So coming to the principle, so first we will see what is this DSC. So DSC is a differential scanning calorimetry, so which is a thermo-analytical technique. So it's a one type of analytical technique used for analysis of your polymers, okay, and thermal transition that takes place in the polymers when they are mixed with the drugs or a pure polymer. Okay, so it's a thermoanalytical technique in which the temperature, the difference in the amount of heat. So the difference in the amount of heat required to increase the temperature of your sample and reference is measured. So okay, so here difference in the amount of heat required, how much amount of heat required to increase the temperature of your sample, or how much amount of heat required to increase the temperature of reference, I mean sample, is measured here. So how much difference of amount heat required. So we are supplying heat to both temperature. So to increase the temperature of your sample and reference, how much heat is required. So we will be measuring it. And this technique was first developed by E.S. Watson and M.J.O. Neal in the year 1962 and introduced commercially in the at the 1963 Pittsburgh Conference on Analytical Chemistry and Applied Spectroscopy. So even though this was developed in the year 1962, so but it became commercial in the year 1963 especially. And the first adiabatic DSC that could be used in the biochemistry was developed by P.L. Privalov and Dr. Mongesad in the 1964 at Institute of Physics and in Georgia. So this is a basic history of your DSC, how it came out, when it came out, and coming to what are the advantages of this technique. So rapidity means the determination how the polymer is undergoing the into the transition process. So we can determine very rapidly and versatile. So we have your FTR and DSC even and XRD. Okay. So compared to all these three analytical techniques, the rapidity of determination is very good and even versatile, and it's simple and easy and speed with which it can be used to see the transition in your material, that is in your samples. And coming to the cost also, so it allows a cost effective determination of certain relevant thermal properties of your material with minimum effort. Okay, and we have some limitations. So compared to the interpretation part, so FTR and especially DSA, so the interpretation is somewhat difficult in this DS, and we will observe some differences between. So when we take one sample in one lab, I mean one DSC study in one sample, one lab, and if we take same DSC in another lab of same sample, so there occurs, I mean, we will observe some differences. So if we are doing a same sample in different labs, the DSC study, so there will be difference. We will observe. That is a major limitation with this technique. Okay. So next we will see the principle of your DSC. What is the main principle? So I already told that. So the reference and sample, the sample whatever need to be tested or checked or analyzed, and a reference are maintained at the same temperature, and during this a thermal event in the sample will be taking place, and the energy required to maintain zero temperature difference between the sample and reference is measured. So how much energy required to maintain your zero temperature difference between sample and reference is measured here. That's the main uh, principle involved in this DSC. And during your thermal event in the sample, the system will transfer heat or I mean transfer either heat or receive the heat from the sample. So in this thermal event, there are two chances. Either the system will transfer heat or it will take the heat from the sample pan to maintain the same temperature in the reference and sample pan. And you know, this DS is a main technique in which the difference in the amount of heat required to heat the temperature of sample and the reference are measured as a function of time. And here, both the sample and reference are maintained at nearly same temperature. Remember, the main thing we have to remember is both the sample as well as reference are maintained at nearly same temperature until your experiment finishes. Okay, and this DSC measures the heats the sample relative to a reference. So that is the main drawback. Principle. So coming to the comparison. So what is the main difference between your DTA and DSC? We will see with help of one like table. So you know DSC is a differential scanning calorimetry and DTA is differential thermal analysis. So DSC, what we are going to study here, the difference is calculated between the amount of heat needed, that is heat flow, how much heat is required to increase the temperature of the sample, and the heat required to increase the temperature of the reference. So how much heat is needed to increase the temperature is measured, whereas in the DTA, so the difference in is calculated within the temperature required by the reference and sample when heat flow is kept same for both the things. So they looking similar, but there is a difference between DSC and TTA. And this DSC works, the instrument based on the DSC mainly used to measure either heat released or absorbed during the transition. So during the transition phase, whether heat is released or absorbed from your material, we will check. Whereas it is based on the to measure the temperature difference. So here we will measure either heat release or absorbed. Whereas in DTA we will measure the temperature difference. So that is the basic difference. Then so this is how your DTA and DSC equipment looks like. Almost all similar, but their principle is somewhat different. And coming to the instrumentation of DS, so mainly we have two types or two basic types of DSC instruments. So one is heat flux DSC and second one is power consumption DS. So we will see what is the difference. So one is heat flux DSC and second one is power consumption, sorry, compensation DSC. So this is how your equipment looks. So we will study in detail about each type. So two types are there. So first one we will take heat flux DSC. What is this heat flux DSC? So we will study the details, how it, what is the construction of this heat flux DSC. So coming to the first, we will talk about the sample holders. Means not only sample holders and a reference. So if you observe in the diagram, so we have a sample pan and a reference pan. Sample pan and reference. And these both pans are made up of aluminum and platinum. So the pans are made up of, here we have, I think you can observe here that in the construction part. So we have two pans here. One pan is for sample, to place your sample, and another pan is to place your reference sample. Both the pans are made up of aluminum or platinum. That is another important point to be remembered here. And these both are placed on an constant N. So if you observe, this red color one is there. So on which your pans, both the pans, that is simple sample pan and reference are placed. So which is called as a constant N. Okay. And your sample and reference holders are connected by a low resistance heat flow path. So both are connected by a low resistance heat flow path. And coming to the sensor, another important point to be remembered. So we have two types of sensor. One is chromel and another one is chromel alumel. So if you observe, so these are the sensors. So one sensor is connected to sample pan and another sensor, if you observe, connected to a reference pan. So we will see what is this important. And if you observe chromo is an alloy which is made up of 90% nickel and 10% chromium. Remember the composition. The chromomel is an alloy of 90% nickel and 10% chromium, whereas chromomel, alumel is an alloy, it's an alloy, but the difference in their composition. So there in chromel, only 90% nickel and 10% chromium, where in case of chromel, alumel, so it contains 95% of nickel, 2% of manganese, 2% of aluminum, 1% of silica. So there is basic, difference in their composition. Okay, thermocouples, that is sample temperature. So and both these sensors are fixed to your thermocouples. So what is this thermocouple? So if you observe, this is a thermocouple. So it is acting as a junction between two different metals that produces a voltage to a temperature difference. So if you observe the thermocouple, so through which your chromel and our sensors are passed to your sample as well as reference. So your thermocouple here is acting as a junction between two different metals, whatever we are using for sample pan and reference. That is a sensors. So next, the furnace is there. What is that furnace? So if you observe, the furnace function is so, and one block for both sample and reference sample. So there will be one block for, because you have to pass the heat. So there will be one block. Okay, heating block. If you observe here, you can observe here. So through which heat can be supplied. So one block will be there for both sample and reference. And temperature controller. So definitely we have to control the temperature. The temperature difference between your sample and reference is converted to differential thermal power, and which is supplied to the heaters to maintain the temperature of the sample and reference at a programmable value. Because it's a fixed value, so uh, the, uh, the temperature difference should be maintained. Okay, so that is the equipment. Then next we will move to second type of your DS, that is power compensation. Here also we will talk about sample holder, sensors, furnace, and temperature. Four things to be remembered in both the equipment. Here also coming to the pans, both the sample pan as well as reference pan are made up of aluminum and platinum. And sensors, if you observe, platinum resistance. So there we talk about thermochem. So different sensors like chromel and chromel alumel, but here the sensors are different in power compensation DSC. So the platinum resistance thermocouples will be there. Separate sensors and heaters for the sample as well as a reference will be there. And same like your first type. So furnace, so separate block for sample and reference cell. And temperature controller will be there. So it supplies different thermal power to the heaters to maintain the temperature of the sample as well as reference at a programmable value. Okay, so this is how your equipment works. So, and coming to the main application of your DS is studying the phase transition, especially in polymers. So you know polymers are showing the phenomenon called that polymorphism. So when they are changing the phase from one phase to another phase, especially like melting, glass transition, or even exothermic decompositions, these all changes we can observe. That is, the transition can be observed with the help of our DSC. And these transitions especially involve energy changes or heat capacity changes. So whatever changes that can be observed can be detected by DSC with a greater sensitivity. Okay, and another important factor that to be controlled here is temperature. So the goal here is to match the melting onset temperature, which is indicated by furnace thermocouple readout to the knowing melting point of standard analyzed by already the melting point of your reference. So based on that, supply the temperature of your sample. Okay, and should be calibrated regularly as close as possible to the desired temperature. So the calibration is very, very important. So whether you are giving a close temperature or not, that should be calibrated before your experimentation. And coming to the heat flow, how much heat you are flowing, that should also be calibrated. Generally, we will pass the heat capacity. So that can be calibrated. I mean, for calibration, we will use an material called sapphire. Sapphire. Okay, one of the material used in the calibration whether you are supplying heat flow correctly or not. And the heat rates we are maintaining here in this DSC is remember the number that is 0.52 to degree centigrade per minute. So per minute we are going to pass the heat with the range from 0.52 to degree centigrade, and similar sample and reference pan weights. Okay, so that is a heat flow and calibrants. So when you are using your calibrants, so it should have some of the ideal properties, like it should be highly purity and accurately known enthalpies. You should know enthalpy of your calibrant, and thermally stable because you are passing some heat, so they should not unstable, they should be stable, and they should be light stable as we are passing the heat, and even so it should be light stable, and it should be non-hygroscopic, and it should be unreactive, it should be inert in nature, especially with your fan and atmosphere where you are working. And metals like indium, stannous, aluminum, and inorganic materials and organic materials are used in this part. Okay, then how to prepare the sample? So like your FTR, you are preparing a sample in the DSC. So how you will prepare, how much quantity of your polymer should be taken is important. So you will take accurately weigh sample nearly 3 to 20 mg, just 3 to 20 mg sample of your material or test sample is enough. And small sample pans are there having capacity of 0.1 ml of inert or treated material metals like aluminum, platinum, and nickel. And we have different pan types. So here, there we have not talked about the different type of your pans, but we have different types of pan configurations. So one is open type pan, second one is pinhole pan, third one is hermetically sealed, that is airtight pan. So depending on your type of your sample you are using, so if it cannot be exposed to directly to temperature, so that can be sealed, hermetically sealed, that is airtight pans are available. So based on your sample, we have open type, pinhole type, or hermetically sealed pan. So based on your sample, we can select. And the same material and configuration should be used for sample and reference. You should not change the whatever the conditions or configurations for both the test and reference. And material should completely cover the bottom of the pan to ensure good thermal contact. Another important precaution to be taken. So your material, whatever you are using in the transition or your study under study, you should have complete contact with the pan so that it will have a good thermal contact. So that is another important thing to be remembered here. Okay, then and should avoid overfilling the pan to minimize the thermal lag from the bulk of the material to the sensor. So should not fill bulk material, means now as our sample size is very less, that is 3 to almost 20 mg. So beyond that range, it should not fill with your sample. Okay, and small sample masses and low heating rates increases the resolution, means your finally graph resolution can be enhanced, means your visibility will be good when your sample is small and low heating rates. So this is how your sample plans will be there, made up of different materials like aluminum, platinum, alumina, nickel, copper, quartz. So you might have seen the sample cells in your UV. So like that, here also you have sample pans. Okay. Then nature of your DSC curves. How? So we will get a curve. So we will see how the curve is getting, and how the nature will be. We will be studying there. So the result of this DSC experiment. So if you plot a graph between either heat flux versus temperature or heat flux versus time. So remember, the curve obtained in your DSC will be obtained when we plot a graph between either heat flux versus temperature or heat flux versus time, either heat fluxes versus temperature or heat fluxes, heat flux versus time. And there are two different conventions. There are two different conventions. So one is, so I told already, either heat absorbed or heat released. Okay. So exothermic reactions will be there, and in that we can observe two types of peaks. One is positive peak and a negative peak. So we will see with the help of graph what is this positive and negative peak. So depending on the kind of technology you are used in the experiment. So we will be seeing exothermic reactions and with the positive or negative peak. And this curve, whatever we obtained, can be used to calculate the enthalpies of your transition. So that it should be calculated. So which is done by your integrating the peak corresponding to a given transition. So the enthalpy of your transition changes, that is the change in their transition, the enthalpy can be calculated by using the formula delta H is equal to Ka. Whereas delta H, your nothing but your enthalpy of transition that has to be calculated, and K is the calorimetric constant, and A is the your area under the peak, area under the peak. So the calorimetric constant varies from instrument to instrument. So it's a constant which is related to instrument. So that is fixed one. So it depends on the your model of your DRC, and can be determined by analyzing a well characterized material of known enthalpy of. So if you know any material transition, that is enthalpy, then enthalpy of your transition, so that can be used as a calorimetric constant. And area under the peak is directly proportional to heat absorbed or evolved by the reaction. So area under means A is nothing but directly proportional to the heat absorbed or evolved by your reaction. And height of the peak, if you observe, is directly proportional to the rate of reaction. The height of the peak is, if the reaction is good, so the height of the peak will be good. Okay, so this is how your DSC curve will be obtained. So if you observe the bottom one, second one, so we will plot a graph between the heat flux versus temperature. So normalized curve setting the initial capacity, if you observe, as a reference, but the baseline, which is dashed one. Okay, so this will be different. Okay, and coming to the factors affecting cost. So which are the factors which will affect this cost? So if you are not getting a proper curve, so we may not predict the transition that takes place in the your polymer. So we have to consider factors. That factors can be studied under two headings. One is the factors related to instrument. So if you are not properly handling the instrument, so that factors may cause effect on the DSC cost. So as well as sample. So if you are not gone for sampling with precaution, so that also causes your that affects your DSC cost. So coming to the instrumentation factors, your furnace heating rate. We already have a fixed heating rate that should be passed into your sample. So if you are not carried properly, again it's a problem. Okay, and recording, then this one, recording or chart speed. So if your recording device or your chart speed is not done properly, again the curve may not be obtained properly. And furnace atmosphere, so it should not, it should be like uh, inert in nature. So because you sometimes you are using hygroscopic materials, so the furnace atmosphere is also very very important. And the geometry of sample holder, that is location of sensors, how your geometry will be there of your sample holder, that is fans, and location of sensors is very very important. And the sensitivity of the recording system, so definitely there will be a recording system, so that sensitivity is very very important, that to be considered. And the composition of your sample content, so what actually it contains, so these are the some of the instrumental factors. Then coming to the sample, so already we have a standard value, so with which we have to prepare a sample. So already we have mentioned we have to use nearly 3 to 20 mg, but that amount of sample is either increase or decrease, again it causes effect on the curve. And the nature of the sample. So how your sample nature is there, and how your sample packing. So we have seen that so open type, pin type, like hermetically sealed. So that's a different type of packing. So that sample packing is also very, very important. And solubility of evolved gas in the sample. So if you are preparing sample, if any gases has evolved, that also considered. And particle size of your sample is also very, very important. And heat of reaction and thermal cut. These are the some of the factors that influences our cause. Okay, this is the general block diagram of your entire DSC. So okay, so if you observe here, temperature recording will be there. So heat flux, how much heat flux we are passing, that can be recorded. You can control the temperature. Okay, so how this totally how this instrument works here, we will see. Okay, and coming to another important point, determination of heat capacity. How much heat capacity is supplied have to determine. For example, a polymer is being heated in your whatever the polymer you take one example. Within this 4 to 4 minutes it may end. So by using same ID, I mean your meeting ID, you can join one more time so that we will finish it. Okay. And when we start heating 2 pans, so for suppose we have placed a polymer of any sample. So what will start? First we will do heating of both the pans. Now the computer will plot the difference in heat output of the two heaters against temperature. That is a plot of heat absorbed by the polymer against temperature. So if you plot a graph between heat flow and temperature, initially you will get a line like this, a line like this. So we will see, and the heat flow is heat, that is Q supplied per unit time. Okay, and now the heating rate is the temperature increase, that is delta T per unit time. So now we have to calculate the heat flow. How we can calculate the heat flow? If you know the heat flow and if you know the time, how much heat flow you are using, and if you know the time to which heat flow is done, so Q by T, so you know we can calculate the heat flow. Okay, so if you know the Q, that is heat flow. Okay, and if you know the T, that is heating rate, that is temperature increase per unit time. So if you know the both parameters, so you can calculate the heat flow. So heating rate is equal to temperature increase by time. So that is can be written as a delta T by T, delta T. Okay, so this is the delta T, and this is a T. And if you know the both parameters, we can calculate. So if you divide this heat flow to heating rate, you can calculate the heat capacity. So if you know this heat flow is nothing but heat by time, and heating rate is nothing but temperature increase by time. So if you know both the heat flow and heat rate, so this is the how we can calculate the heat capacity. So in this equation, thus both the T get cancelled and Q by delta T. Okay, Q by delta T. So by this we can calculate the heat capacity. Heat capacity. Okay. So we will stop here. We'll end and we'll join one more time so that we will finish it. Okay. So join immediately.